Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, R-CADT, presents the conference. Data classification based on mathematical programming. Clustering, segmentation, and identification. It can be said that all the basic methods of predictive analytics are based on mathematical programming, and that in practice they are all characterized by minimizing a penalty function, usually least squares, to estimate the parameters of the different methods. The process of classifying known or unknown entities consists of 3 steps. Cluster analysis, definition of the groups, clusters, categories, segments, and so on, into which entities can be grouped. Segmentation or classification, determination of the mathematical rules that each entity, or sample, must comply with to be part of a segment or a class or a group or a cluster. Identification, classify new entities into already defined entity. Note, the names given to these processes are specific to this material, as there is no universal definition that differentiates them. The power of computing and the large memory of computers today offer a great opportunity for information processing and storage. But information is not knowledge, and methods are needed that allow information to be passed on to knowledge. Automatic knowledge extraction from storage data then becomes a major challenge for the information technology industry. Data classification is a supervised learning strategy that analyzes the organization and categorization of data in distinct classes. Generally, a training set, in which all objects are already associated with known class labels, is used by classification methods. The data classification algorithm works on this set by using input attributes and builds a model to classify new objects. In other words, the algorithm predicts output attribute values. Output attribute of the developed model is categorical. There are many applications of data classification in finance, healthcare, sports, engineering and science. Data classification is an important problem that has applications in a diverse set of areas ranging from finance to bioinformatics. The main goal is to generate a separating hypersurface which maximizes the margin and produces good generalization ability. A broad range of methods exists for data classification problem including decision tree induction, Bayesian classifier, artificial neural networks, ANN, support vector machines, SVM, discriminant analysis, probit and logit, mathematical programming, MP. The data classification problem is based on 2 parts, training and testing. Determining the characteristics of data points belonging to a certain class and differentiating them from data points belonging to other classes are the objectives realized during the training part. Like test sets, validation sets wear out when used repeatedly. The more times you use the same data to make decisions about hyperparameter configuration or other model enhancements, the less confident you are that your model will generalize well to new, invisible data. Therefore, it is a good idea to collect more data to update the test suite and the validation, or training, set. Below are some applications of data classification. There are multiple cases of application of the classification. The image presents user classifications, according to an activity, in this case the programming language used. Clustering, segmentation, and identification. It can be said that all the basic methods of predictive analytics are based on mathematical programming, and that in practice they are all characterized by minimizing a penalty function, usually least squares, to estimate the parameters of the different methods. The process of classifying known or unknown entities consists of 3 steps. Data classification based on mathematical programming. Mathematical programming methods for pattern classification emerged in the 1960s, gained popularity in the 1980s, and have grown drastically since. A very good review of this type of models is in Lee, Linear and Nonlinear Separation of Patterns by Linear Programming. Several classification models based on mathematical programming are presented, including linear programming, mixed integer programming, nonlinear programming, and support vector machines. There are 2 types of approaches. The application of MP to hypothesis-based methods on the probabilistic behavior of the data. This is direct since all parametric methods are based on maximizing the likelihood function of the sample. Non-parametric approaches, which has an advantage to analyze datasets over methods that require assumptions about the probability distribution of the data. This methods use MP to determine the coefficients of linear, nonlinear or mixed linear, discriminant functions or support vector machines, and they obtain the coefficients using different objective functions, minimizing the sum of the distances to the separating hyperplanes, the maximum distance of an observation to the hyperplane, and other measures of badness of fit or maximizing measures of goodness of fit. Given a set of training samples, each marked as belonging to a group of several categories, mathematical rules or equations to follow to classify a new entity into a segment are established. The results of these models are the mathematical rules for classifying entities. Non-probabilistic binary classifier. Generalized support vector machine, GSVM. For the case of binary segmentation, two segments, GSVM is a representation of the entities as points in a multidimensional space in which the samples of the different categories will be separated in such a way that they are divided by a vector that separates two categories so that the gap space is as wide as possible. New entities are assigned to a cluster in that same space based on which side of the gap they are on. Probabilistic binary classifier. In statistics, binomial regression is used to model a binary dependent variable, 0 or 1. There are at least three methodologies to deal with the problem. Discriminant analysis. Logistic model, logit model, probit model. These models maximize the likelihood of the sample, maximum likelihood, and differ in their probabilistic assumptions. The objective in data classification is to assign data points that are described by several attributes into a predefined number of classes. The use of hyperboxes for defining boundaries of the sets that include all or some of the points in that set can be very accurate on multi-class problems. When the boundaries of these hyperboxes will overlap, it is necessary, more than one hyperbox could be used to represent a class. Thus, two boxes are constructed to eliminate this overlapping. A very important consideration in using hyperboxes is the number of boxes used to define a class. If the total number of hyperboxes is equal to the number of classes, then the data classification is very efficient. On the other hand, if there are as many hyperboxes of a class as the number of data points in a class, then the data classification is inefficient. The data classification problem based on this new idea is built in two parts: training and testing. Determination of the characteristics of the data points that belong to a certain class and differentiation them from the data points that belong to other classes are the targets done during the training part. Thus, boundaries of the classes are formed by the construction of hyperboxes in the training step. After the distinguishing characteristics of the classes are determined, then the effectiveness of the classification must be tested. Predictive accuracy of the developed model is performed on a test data set during the test part. Cluster sample. The image presents the sample of points available for clustering. In this case there are 4 types of points, to determine the groups, which could be 2, 3 or 4. The result of a grouping process is not exact and depends on the modeler's criteria. In the example, depending on many factors, such as the scale of the sample, the answer could be to group into 1, 2 or 4 groups. Cluster analysis, definition of the groups, clusters, categories, segments, and so on, into which entities can be grouped. In this case, hyperplanes or support vector machines are used. Using hyperplanes or using hyperboxes. Using hyperboxes to define the boundaries of sets, that include all or some of the sample points, can be very accurate for problems of various types. When the boundaries of these hyperboxes overlap, more than one hyperbox could be used to represent a class. Therefore, 2 boxes are built to eliminate overlap. A very important consideration in using hyperboxes is the number of boxes used to define a class. If the total number of hyperboxes is equal to the number of classes, data classification is very efficient. On the other hand, if there are as many hyperboxes as the number of data points, then data classification is inefficient. Thus, boundaries of the classes are formed by the construction of hyperboxes in the training step. After the distinguishing characteristics of the classes are determined, then the effectiveness of the classification must be tested. Predictive accuracy of the developed model is performed on a test data set during the test part. using hyperplanes or using hyperboxes, using hyperellipsoids or using hyperboxes. Kernel functions are mathematical tools used in machine learning and statistics to measure similarity between data points, often by implicitly mapping them into a larger dimensional space. The kernel trick allows algorithms to handle complex, nonlinear relationships without the computational cost of explicitly transforming data. Common examples include linear, polynomial, and Gaussian radial base function, RBF, kernels, each suitable for different data structures and relationships. The kernels are interpreted as scalar products in high-dimensional spaces. With the number of dimensions, the complexity increases, obtaining algorithms with great expressive capacity, but with the problems of estimation and possible overtraining of the model. The table presents examples of the most common kernel functions. However, it should be noted in general that any user can create their own kernel functions. However, overperforming kernel functions can lead to interpretation issues in the estimated parameters and/or overestimation. Using kernel functions may be a good habit to linearize the models. The kernel function then transforms the original nonlinear space into a new projected linear space. If you want to use more complex criteria, you can use kernel functions to get various types of transformations from nonlinear spaces to linear spaces. The graph uses the separation of spaces of a nonlinear sample, in two segments, the valid dotted space, in blue, and the outlier space, rejected points in red. This process is called anomaly detection. It refers to the identification of elements or events that do not fit an expected pattern, or other elements present in a dataset, which may be interesting or data errors that require further investigation. The image shows the mathematical formulation of the SVDD problem. The image shows the mathematical formulation of the PSVM problem. The following questions may be answered. Identification of unusual data records that can be error in data, medical problems, errors in a text, intrusions by hackers. The anomalies are also called outliers, novelties, noise, deviations, and exceptions. The mathematical methodologies used are machine learning, multi-state Kalman filter, Bayesian inference, data envelopment analysis. Identification. Identification is the model that aims to classify new entities into already defined clusters. This process is necessary since the clustering and classification processes are carried out on a known sample, and the objective in many cases is to identify the group to which a new sample belongs. Some examples are to identify the type of new customer, to assign the quota, and the type of new medical imaging, such as a scan, to determine if the patient is sick. Nowadays, segmentation classes or groups are often used in various fields. In such cases, we usually use grouping or clustering techniques. Especially, one of the emerging problems is in the biological and medical areas and is the identification of new subtypes of biological samples or patients, and possibly, we often need to find new subtypes of the known clusters. For new clusters, typical methods might mix the labels of known classes, resulting in an incorrect interpretation of the identified clusters. Depending on the case, it might be appropriate to repeat the clustering algorithm or implement a variation to generate the new clusters. In the case of a patient or a misclassified sample, the mathematical problem may be simpler, but depending on the field of study, it could be very serious. Below, the processing of a database is presented, from the process of capturing and cleaning a piece of data, that is, its classification, to the identification of a new sample. The first stage is related to the selection of the databases that will be included in the original sample. In this case, it is proposed to obtain data from the company, syndicated databases and data from other media. The second stage is related to structuring the data model and loading the unified data to produce the original database already loaded. Next, you need to clean up the database. This involves deleting records with errors or outliers. Once a clean working database is obtained, the next step is to implement the clustering and classification models. This process produces a classification model for each segment for the data that has been processed, for example, customers and/or competitors. This completes the processing of the original database, from the process of capturing and cleaning a piece of data, to the clustering and classification models, ready for the identification of a new sample. Identification involves incorporating three elements into the process: new database, model for identifying new data, and classification of new data. Depending on the data, the identification model can tolerate errors. For example, identifying a customer is not the same as identifying a scanned image. Given a set of entities, cluster analysis looks for homogeneous or separate groups. Homogeneity means that entities within the same cluster must resemble each other, and entities in different groups must differentiate from each other. The results of these models are the number of clusters or groups, and the classification of known entities in groups. A clustering problem can be the CMyQ that minimize the sum of the Euclidean distances between the entities of a group. This formulation corresponds to a quadratic mixed programming problem. Another version, the CDG problem, minimizes maximum distance within groups. This formulation has the advantage that it corresponds to a linear mixed programming (MIP) problem that is easier to solve than the previous one. In both cases, the size of the mathematical problem grows rapidly with the number of clusters, n, and the number of objects, m. Therefore, advanced methodologies are also required for its solution. Multi-class classification. Data classification is a supervised learning strategy that analyzes the organization and categorization of data into different classes. Typically, classification methods use a training set, in which all objects are already associated with known class tags. The data classification algorithm works on this set by using input attributes and creates a model to classify the objects. In other words, the algorithm predicts the values of the output attributes. Multi-class data classification via mixed integer optimization is the document used in this part of the conference. The objective in multi-class data classification is to assign data points that are described by several attributes into a predefined number of classes. The use of hyperboxes for defining boundaries of the sets that include all or some of the points in that set can be very accurate on multi-class problems. When the boundaries of these hyperboxes will overlap, it is necessary. More than one hyperbox could be used to represent a class. Thus, two boxes are constructed to eliminate this overlapping. A very important consideration in using hyperboxes is the number of boxes used to define a class. If the total number of hyperboxes is equal to the number of classes, then the data classification is very efficient. On the other hand, if there are as many hyperboxes of a class as the number of data points in a class, then the data classification is inefficient. The data classification problem based on this new idea is built in two parts: training and testing. Determination of the characteristics of the data points that belong to a certain class and differentiation them from the data points that belong to other classes are the targets done during the training part. Thus, boundaries of the classes are formed by the construction of hyperboxes in the training step. After the distinguishing characteristics of the classes are determined, then the effectiveness of the classification must be tested. Predictive accuracy of the developed model is performed on a test data set during the test part. The goal of data classification is to map data points described by various attributes in a predefined number of classes. Using hyperboxes to define the boundaries of sets, which include all or some of the points, can be very accurate in problems of various types. If necessary, more than one hyperbox could be used to represent a class, as shown in the figure. If the classes indicated by square and circular data points are represented by a single hyperbox, the boundaries of these hyperboxes will overlap, therefore two boxes are constructed to eliminate this overlap. Mathematical programming is applied on a set of 16 data points in 4 different classes given in the figure. Data points can be represented by two attributes, 1 and 2. There are a total of 20 data points, 16 of them were used in training and 4 of them in testing. The training problem classified the data into 4 classes using 5 hyperboxes as shown in the figure. It is interesting to note that class 1 requires 2 hyperboxes, while the other classes are represented by a single hyperbox. The reason for having two hyperbox for class 1 is that a single hyperbox for this class would include one of the data points that belong to class 3. To eliminate inconsistencies in the training dataset, the method included one more box for class 1. A very important consideration in using hyperboxes is the number of boxes used to define a class. If the total number of hyperboxes is equal to the number of classes, then the data classification is very efficient. On the other hand, if there are as many hyperboxes of a class as the number of data points in a class, then the data classification is inefficient. The data classification problem based on this idea is built in two parts: training and testing. Determination of the characteristics of the data points that belong to a certain class and differentiation them from the data points that belong to other classes are the targets done during the training part. Thus, boundaries of the classes are formed by the construction of hyperboxes in the training step. After the distinguishing characteristics of the classes are determined, then the effectiveness of the classification must be tested. Predictive accuracy of the developed model is performed on a test data set during the test part. The figures present the sample and the results of the multi-class classification. Training part studies are performed on a training data set composed of several data point I. The data points are represented by the parameter AIM that denotes the value of attribute M for data point I. The class K that the data point I belongs to are given by the set DIK. Each existing hyperbox L encloses several data points belonging to the class K. Moreover, n bounds, lower and upper, of each hyperbox is determined by solving the training problem. The following MILP problem models the training portion of the data classification method using hyperboxes. To eliminate the unnecessary use of hyperboxes, their unnecessary existence is penalized with a small scalar c. The objective function of the MILP problem is to minimize the misclassifications in the dataset with the minimum number of hyperboxes. The lower and upper limits of the boxes are given in equations 2 and 3 and are determined by the data points that are enclosed within the hyperbox. Equation 4 enforces the bounds of hyperboxes that exist if and only if this hyperbox is assigned to a class. Equation 5 is used to relate the two continuous variables that represent the bounds of the hyperboxes. The position of a data point with respect to the attribute boundaries for a hyperbox is given in equations 6 and 7, one for the lower bound and one for the upper bound. The binary variables help to identify when a data point is within a hyperbox. Since these constraints establish a relation between continuous and binary variables, an arbitrarily large parameter, q, is included in these constraints. Equations 8 and 9 state that each data point must be mapped to a single hyperbox, L, and to a single class, K. The equivalence between these equations is given in equation 10, indicating that if there is information in the K class, then there must be an L hyperbox to represent the K class and vice versa. The existence of a hyperbox implies the assignment of that hyperbox to a class as shown in equation 11. Equation 12 indicates that if a class is represented by a hyperbox, there must be at least one data point within that hyperbox. Equation 13 indicates that if a hyperbox represents a class, there must be at least one data point within that class. Equation 14 represents the condition of a data point that is within the boundaries of a box for all of its attributes, so it must be in the box as shown in equation 15. When a data point is assigned to a class of which it is not a member, a penalty is applied as indicated in equation 16. Equation 17 fixes the non-negativity and integrality of the decision variables. By using this MILP formulation, a training set can be studied, and the bounds of the classes are determined for a data classification problem. This example was tested for different data classification models to compare results and measure performance. The table shows the models examined. The figure shows the misclassification issues identified as A, B, C, and D. The multi-class data classification problem can be effectively modeled as a MILP problem. One of the most important features is the use of hyperboxes to define class boundaries that enclose all or some of the data points. If necessary, more than one hyperbox is created for a given class. In addition, the good construction of the boundaries of each class provides the absence of misclassifications in the training model, which improves its accuracy. The classification problem in two-group discriminant analysis. There have been numerous attempts to solve classification problems using mathematical programming. A survey of classification methods using mathematical programming was published by Joachim Staller and Stamm. The title of the paper was, Mathematical Programming Approaches for the Classification Problem in Two-Group Discriminant Analysis. The mathematical programming approach to data classification was introduced in the early 1980s. Since then, numerous mathematical programming models have appeared in the literature. These include, minimize the maximum external deviation, minimize the weighted sum of the exterior deviations, minimize a measure of exterior deviations. While most of these methods are modeled linear programming, LP, problems to optimize a distance function, and a mixed integer programming, MIP, problems to minimize misclassifications. Mathematical programming, MP, methods have certain advantages over the parametric ones. They are free from parametric assumptions. Moreover, varied objectives and more complex problem formulations can easily be accommodated. On the other hand, getting a solution without any discriminatory power, unlimited solutions, and a requirement of excessive computational effort are some of the problems of these methods. The discrimination between the elements of two disjoint sets of points, A and B, is a classic problem of pattern classification that is solved by a non-parametric methodology that uses linear programming as a basic computational tool. The sets of points A and B are linearly separable if and only if there exists a hyperplane in which the points of the sets A and B are on opposite sides of the hyperplane that can be easily constructed by solving a single linear program, as Mangasarian did in 1965. The document, Pattern Recognition via Linear Programming, Theory and Application to Medical Diagnosis, presents a resume of the studies of Mangasarian. The document Classification and Diseases Prediction via Mathematical Programming presents several classification models based on mathematical programming approaches. An overview of various mathematical programming approaches is presented, including linear programming, mixed integer programming, nonlinear programming, and support vector machines. Several general-purpose, optimization-based classification models are analyzed that are suitable for developing predictive rules for large heterogeneous datasets. The models simultaneously incorporate the ability to classify any number of distinct groups, the ability to incorporate heterogeneous types of attributes as input, a high-dimensional data transformation that eliminates noise and errors data, the ability to incorporate constraints to limit the rate of misclassification, and a reserved judgment region that provides a safeguard against overtraining, which tends to lead to high misclassification rates from the resulting predictive rule, and successive multistage classification capability to handle data points placed in the reserved judgment region. To illustrate the power and flexibility of the classification model and solution engine, and its multi-group prediction capability, application of the predictive model to a broad class of biological and medical problems is described. Linearly separable method of pattern separation. The general problem being analyzed is related to a sample of observations that must be classified into at least two segments. The classification of the segments is limited by two hyperplanes. Hyperplanes should be chosen from all possible ones, maximizing the distance to space-limiting hyperplanes, as shown in the image. The models considered, with their corresponding summarized algebraic formulation, are listed below. MSD, minimize the sum of deviations. L1 norm distance, MMD, minimize the maximum deviation. L'infinite norm distance, MZD, minimize the sum of interior distances. LP norm classification. MSD error, minimize the sum of deviations including a gap. MSD BNT, minimize the sum of deviations, bounded and non-trivial. Hybrid model, Glover et al. RLP, robust linear programming, minimizes the average of the deviations. BALP. Asperkov and Stamm, 1997, propose a LP model to solve the two-group classification problem where the attributes are binary. In this case, the training data can be partitioned into multinomial cells, allowing for a substantial reduction in the number of variables and constraints. The model shown below is the LP model of minimizing the sum of deviations for two-group classification with binary attributes. MSDLP, minimize the LP norm objective criterion. MMLPEC. Mangasarian formulates the problem of minimizing the number of misclassifications as a linear program with equilibrium constraints, LPEC, minimizing the number of misclassifications. The table presents a summary of the methods described and is a sample of the variety of approaches that can be handled in mathematical programming. Multi-class data classification. There have been numerous attempts to solve classification problems using mathematical programming. A survey of classification methods using mathematical programming is published by Joachim Staller and Stamm. In Mathematical Programming Approaches for the Classification Problem in Two-Group Discriminant Analysis. The mathematical programming approach to data classification was first introduced in early 1980s. Since then, numerous mathematical programming models have appeared in the literature. These include minimizing the maximum exterior deviation, minimizing the weighted sum of exterior deviations, minimizing a measure of exterior deviations while maximizing a measure of interior deviations, minimizing the number of misclassifications, and minimizing a generalized distance measure. Most of these methods modeled data classification as linear programming, LP, problems to optimize a distance function. Contrary to LP problems, mixed integer programming problems that minimize the misclassifications on the design dataset are also widely studied. The mathematical programming approach to data classification was first introduced in early 1980s. Since then, numerous mathematical programming models have appeared in the literature. These include minimizing the maximum exterior deviation, minimizing the weighted sum of exterior deviations, minimizing a measure of exterior deviations while maximizing a measure of interior deviations, minimizing the number of misclassifications, and minimizing a generalized distance measure. Most of these methods modeled data classification as linear programming, LP, problems to optimize a distance function. Contrary to LP problems, mixed integer programming problems that minimize the misclassifications on the design dataset are also widely studied. Mathematical programming methods have certain advantages over the parametric ones. For instance, they are free from parametric assumptions and weights to be adjusted. Moreover, varied objectives and more complex problem formulations can easily be accommodated. On the other hand, obtaining a solution without any discriminating power, unbounded solutions and excessive computational effort requirement are some of the problems in mathematical programming-based methods. Kohler surveys considerations for mathematical programming models and discriminant analysis, the potential problems in mathematical programming formulations. Since MIP methods suffer from computational difficulties, the efforts are mainly focused on efficient solutions for two-group supervised classification problems. Although ways to solve a multi-class data classification problem exist by means of solving several two-group problems, such approaches also have drawbacks including computational complexity resulting in long computational times. The discrimination between the elements of two disjoint sets of points, A and B, is a classic problem of pattern classification that is solved by a non-parametric methodology that uses linear programming as a basic computational tool. The sets of points A and B are linearly separable if and only if there exists a hyperplane in which the points of the sets A and B are on opposite sides of the hyperplane that can be easily constructed by solving a single linear program by Mangasarian in 1965. Multi-surface pattern separation. The paper Pattern Recognition via Linear Programming, Theory and Application to Medical Diagnosis is fundamental in the study of mathematical programming used in the classification of medical images. The leader of the team was Mangasarian during the decade of the 60s of the last century. Medical imaging can be classified according to its technique, such as X-rays, CT scans, MRIs, ultrasounds, and nuclear medicine, or according to its function or application. They are also classified by the type of information being analyzed, such as imaging modalities or clinical pathologies. The original image is in 2D or 3D, and the analysis process consists of determining for each point of the matrix image its characteristics to make the appropriate decisions, the doctor's diagnosis. The size of the transformed image depends on the computational power, which increases day by day, allowing algorithms of greater dimensionality. Pattern recognition. It is the automated recognition of patterns and/or regularities in data. The mathematical methodologies used are machine learning via artificial neural networks, and mathematical programming. Multi-surface method of pattern separation. Since, in general, sets A and B are not linearly separable, Mangasarian, 1968, resort to the technique of multi-surface pattern separation whereby a piecewise linear separating surface is constructed sequentially by means of a finite number of pairs of parallel planes as follows. Any two parallel hyperplanes in a multi-dimensional real space determine three disjoint regions. Using LP, we determine two such hyperplanes, as close together as possible, so that only the region between contains points from both sets A and B. Once this is done, the outer points are discarded and we repeat the process with the inner points and so on, until what is left is linearly separable. The methodology is based on iterative segmentation of the surface that must be divided into two clusters. The image presents the complete sample. Initially, the space is divided into two segments, using a two-group selection method. The sample is divided into three types of dots. The blue dots belong to segment A, the red dots belong to segment B, and the gray dots that are not defined to which segment they belong. The space is divided by a central area that is bounded by two lines indicating the area of segments to be defined. The undefined center area will be divided into new segments, using the already defined segments as the boundary condition. From this point on, the cycle is restarted to obtain a solution with only two segments. The cycle will be carried out until the desired solution is obtained. The process will continue dividing the new space into two new segments. In each cycle there will be a space that cannot be perfectly divided into two, until the smallest segment is reached for which a new iteration is not necessary, since the space to be divided is empty. The image presents the curve of the linear parts resulting from the process, which approximates a division of space that could be nonlinear. Support vector machines. Machine learning, ML, is the scientific study of algorithms and statistical models that use computer systems to progressively improve their performance on a specific task. One of the foundations of ML is the support vector machines, SVM, that have their origin in the work on the theory of statistical learning and were introduced in the 90s by Vapnik and his collaborators. Although SVMs were originally intended to solve binary classification problems, they are currently used to solve other types of problems: regression, clustering, multiple classification. There are also several fields in which they have been used successfully, such as computer vision, character recognition, text and hypertext categorization, protein classification, natural language processing, time series analysis, etc. Let's consider a binary classification for a sample that depends on several factors: weight, volume, route, type of load, and that can be classified into success and non-success. The problem is to separate the space by means of a hyperplane, support vector machine, SVM, that divides the objects, entities, samples, into success and non-success. The mathematical problem is related to the fact that, in certain cases, there can be an infinite number of hyperplanes that can divide space, and therefore it is necessary to select the best of them. SVM determines the optimal hyperplane as the one that maximizes the distance from the closest point of each group to the SVM. Therefore, determining the SVM corresponds to an optimization problem. Let's consider a separable set of two types of objects with XID components. An SVM can be defined as a linear function that can separate such a set without error, where Wi are real coefficients, components of the vector W, B is a real coefficient, and the operator Wx represents the point product between W and X. The algebraic formulation is in the picture. La distancia entre un hiperplano de separación dxy un vector x viene dada por el operador de norma de un vector xyw. El vector k junto con el parámetro b define el hiperplano dx, y que tiene la propiedad de ser perpendicular al hiperplano considerado. Given the definition of a separation hyperplane, the distance must be less than any other distance to points within the edge. Finding the optimal hyperplane W is equivalent to maximizing the distance dx. The distance between a separation hyperplane dx and a vector x is given by the norm operator of a vector x and w, the vector that together with the parameter b defines the hyperplane dx, and which has the property of being perpendicular to the hyperplane considered. Given the definition of a separation hyperplane, the distance must be less than any other distance to points within the edge. Finding the optimal hyperplane W is equivalent to maximizing the distance dx. Therefore, maximizing the margin dx is equivalent to minimizing the norm of W, which is equivalent to minimizing the sum to the square of the components of W, which corresponds to a quadratic programming problem. If the above problem has a feasible solution, the problem is called a separable classification problem. This hyperplane is called the hard margin support vector, hard SVM. If it does not have a feasible solution, it implies that there is no hyperplane that can divide space into two parts, in such a way that it groups all objects of the same type in the same semi-space. In that case, the classification problem is called quasi-separable. It sets out to solve a problem that includes a fit error C, a constant large enough to control the degree to which the non-separable penalty term influences the minimization of the norm. This hyperplane is called the smooth margin separation support vector, soft SVM. Correlation clustering. Many computer vision tasks involve grouping a set of observations into single entities. A powerful formulation for such tasks is the weighted correlation clustering. The document A Bender's Decomposition Approach to Correlation Clustering presents the theory and its application to use Bender's decomposition to solve the correlation clustering (CC) problem. Many computer vision tasks involve grouping a set of observations into single entities. A powerful formulation for such tasks is the weighted correlation clustering, CC. CC is defined in a sparse graph with true value edge weights, where nodes correspond to observations and weighted edges describe the affinity between pairs of nodes. In image segmentation in superpixel graphics, the nodes correspond to superpixels, and the edges indicate the adjacency between them. The weight of the edge between a pair of superpixels is related to the probability, defined by a classifier, that the two superpixels belong to the same entity. This weight is positive if the probability is greater than 1 and negative if it is less than 1. The magnitude of the weight is a function of the confidence of the classifier. Some correlation clustering for problems in computer vision. Classical work that use Bender's decomposition. The work is based on Cordeau, which solves a MILP over a set of fixed charge variables and a larger set of fractional variables associated with constraints. Mignati and Wang are used in the approach instead of standard Bender's. Bender's is used in computer vision with the purpose of estimating the position of several people. The image shows correlation clustering for tracking. The image shows correlation clustering for motion segmentation. Decision trees are a popular class of predictive models because of their interpretability and good performance on categorical features. However, they are not always robust and tend to reveal the data. In addition, if they grow up, they lose interpretability. The document Optimal Decision Trees for Categorical Data via Integer Programming presents a mixed integer programming formulation to construct optimal decision trees of a pre-specified size. The special structure of categorical features is considered and combinatorial decisions, based on subsets of feature values, are allowed at each node. The approach can also handle numerical features across thresholds. Experiments show that good accuracy can be achieved using moderately sized training sets. Decision Tree, DT, is a decision support tool that uses a tree-like model of decisions and their possible consequences, including chance event outcomes, resource costs, and utility. It is one way to display an algorithm that only contains conditional control statements. DTs are commonly used in operations research, specifically in decision analysis, to help identify a strategy most likely to reach a goal, but DTs are also a popular tool in machine learning. DTs are like flowcharts in that they apply a sequence of binary tests or decisions to predict the output label of the input data. As they can be easily interpreted and applied by non-experts, DTs are considered one of the most widely used machine learning and data analysis tools. DTs often result in feature selection, as only a portion of the input is typically used in the decision-making process. In addition, they can work directly with numerical and categorical data, which is not the case with numerical classifiers such as linear classifiers or neural networks, because they require the data to have a real, and ordinal, value. Formally, a DT is defined by topology, binary tests applied on each decision node, and labels assigned to each final sheet, which are indicated by the colors white and gray. The chart shows several decision tree topologies. As a concrete example, consider the tree in the figure applied to binary vectors into two groups, A1, A2, A3, A4, and A5, A6, corresponding to two categorical features in the original data representation. The branching decision at node 1 is based on whether one of A1 or A2 equals 1. If true, a given data sample is routed to the left, otherwise, that is, if A1 and A2 are equal to 0, the sample is routed to the right. The branching at nodes 2 and 3, two children of node 1, are analogous and are shown in the picture. We can see that data sample A1 equal to 1, 0, 0, 0, 0, 1, is routed to leaf node 1 and data sample A2 equal to 0, 0, 1, 0, 1, 0, is routed to leaf node 3. The labels of the leaf nodes are denoted by the colors white and gray. We therefore have the following integer programming, IP, formulation, where C in the objective, 8a, is a constant weight chosen in case of class imbalance. For instance, if a training set has twice as many good examples as bad examples, it may be worth considering setting C equal to, so that every correct classification of a bad data point is equal to 2 correct classifications of good data points. LP relaxation, presented above, is a correct formulation but is quite weak, and computational performance can be improved. Some ideas can be analyzed that help reduce the size of the problem, break symmetry and strengthen the relaxation of linear programming. The document learning optimal classification trees using a binary linear program formulation. Presence. The problem of learning optimal classification trees as a binary linear program. This approach finds a classification tree of a given depth that minimizes the total classification error for a given dataset. The problem of learning classification trees is formulated as a binary linear program. This approach, exemplified by methods such as BinOCT, aims to find a classification tree of a given depth that minimizes misclassification error. Key aspects of this formulation include binary decision variables, the decisions in each internal node and the predictions in the leaf nodes using binary variables. The above formulations use continuous or integer decision thresholds. Reduced dependence on data size. A significant advantage of the binary formulation is that the number of decision variables can be largely independent of the number of rows of training data. It depends more on factors such as the depth of the tree and the number of unique feature values. This addresses a limitation of older formulations that scaled poorly with large datasets due to the creation of variables and constraints for each row of data. Optimization objective. The objective function of the binary linear program is to minimize misclassification error, maximizing the accuracy of the learned tree. Constraints. They ensure the logical structure of the classification tree, forcing each row of data to reach exactly one leaf node and that decisions on internal nodes are consistent with the data. The image shows the algebraic formulation of the BinOCT model, which aims to minimize the total classification error. Conjoint analysis. Conjoint analysis, CA, also called compositional modeling of multiple attributes, is a statistical technique originated in mathematical psychology. Today it is used in many of the social sciences including marketing, product management, and operations research. The document The Robust Linear Programming Technique for Multidimensional Analysis of Preferences, Presence. The Linear Programming Technique for Multidimensional Preference Analysis, LinMAP, is one of the multi-attribute decision-making, MADM, techniques that has been implemented in sharp and diffuse environments. Robust optimization obtains a solution that is feasible in all circumstances that arise due to parameter uncertainty. Conjoint analysis determines which combination of a limited number of attributes is preferred by respondents. It is frequently used to check customer acceptance of new product designs and to assess the attractiveness of advertisements. CA has been used in product positioning, but there are some problems with the application of the technique. In the case of marketing, the steps to follow are: first, collection of information. Selection of products/services. Selection of features to test. Show product combinations to potential customers. Respondents rank combinations. Respondents are shown a set of products, prototypes, mock-ups, or portraits. Each example is similar enough to the other that consumers see it as a substitute, but different enough that they can clearly determine a preference. Each example is made up of a combination of product features. The result is a range of preferences. Second, analysis. Customer sample data is analyzed as a whole. The analysis will produce the features most preferred by customers. Variance analysis, or linear programming, techniques are used to create utility functions, which indicate the perceived value of the feature and how sensitive customers' perceptions and preferences are to changes in product features. In classical mathematical programming, it is often assumed that the input data is precisely known. If the data takes a different value from the nominal values, the optimal solution estimated using the nominal data might not be optimal or even infeasible. In real applications, there are numerous problems with uncertain parameters. An optimization problem can be very sensitive to data uncertainties, therefore, it may result in an inapplicable solution. The approach developed to overcome data uncertainties is robust optimization, where the decision maker attempts to determine an optimal solution for the worst-case value of the target function, which satisfies any data from the given uncertainty set. In Figure A, defined by traditional optimization, is the best in terms of optimality, but it can change widely and result in an unworkable solution. On the other hand, Solution B, determined by robust optimization, is moderately good in terms of optimality and good in terms of robustness. The solution changes, but it never results in an unfeasible solution. Robust optimization provides the opportunity to input random data into the model without knowing their probability distributions and only by determining uncertainty sets. This facilitates many approaches for robust optimization. Some are: Soyster proposed a linear optimization model to find a solution that remains feasible for all data belonging to a convex set. The model is extremely conservative. Mulvey presented an approach that merges goal programming with scenarios from the input data. Bental and Nemorowski together with El Gawi and Lebray, assuming that data are uncertain in elliptical sets, presented efficient algorithms for solving convex optimization models. Since their robust counterparts are quadratic and conic models, they cannot be used directly in discrete optimization models. Bertzimas and Sim presented a different approach to managing the level of conservatism, which results in a linear optimization model. Therefore, it is applicable in discrete optimization models. The image presents the linear optimization problem, which can be reviewed in the article. The image presents the optimization problem proposed by Soyster. The image presents the optimization problem proposed by Bertzimas and Sim. Each MCDM technique focuses on a particular aspect. LinMap can define both the weights of the attributes and the order of classification of the alternatives, so it is presented as a multidimensional method. In LinMap, all preference information is precisely known. It does not consider the impact of data uncertainties on the quality and feasibility of the solution. However, most real-world problems involve uncertain data, and uncertainty can render the optimal solution meaningless entirely. LinMap, including robust optimization approaches that are used to capture robustness in the LinMap method, looks for a positive ideal solution and a weight vector that remains feasible with respect to data changes. Figure shows the algorithm about the decision-making process with the LinMap method. The computer-based mathematical modeling is the greatest invention of all times. Herbert Simon Nobel Prize in Economics, 1978 for his pioneering research into the decision-making process within economic organizations. Thank you for your attention.